Okay, good morning, guys. I am attempting to create 3 videos for you for Chapter 8, considering that we have that exciting week coming up with homecoming at the end of it. But let's just go ahead and get started in talking about the chapter on energy and metabolism. This is Chapter 8. And you'll notice here that it says to redefine growth and metabolism. Remember, growth we would just consider to mean growing of a cell, growing of a body, growing in general and developing throughout life. But in reality, we want to be able to talk about growth as the ability for a cell to take the energy from the environment and be able to grow, repair, and reproduce in terms of metabolism. So it's important that we understand that growth has to do with the energy that's available, and that metabolism is cellular work, and the work of growth, repair, and reproduction has everything to do with the energy that's available. So we want to sort of focus in on, keeping this at the forefront of the discussion in this chapter. So obviously energy for life is needed. We all undergo cellular respiration that drives the cellular economy. We say economy because energy is sort of like the monetary unit for doing anything or getting any work done inside of the cell. So being able to breathe in and to respire and to go through that entire process is driving the ability of our cells to sort of dole out the energy into manageable packets, or essentially take that energy and pay for the cellular work that's going to be done. And we learn how to do this by extracting sugars, or extracting energy that's stored in sugars, and again, that energy is used for cellular work. And I'll draw your attention to, to this sort of little diagram here because it's illustrating the idea that in terms of metabolism, as you can see up here, this is a metabolic pathway. Nothing that we talk about, nothing that we do, and anything that has to do with growth and metabolism, it is a pathway. There are very few processes in our bodies that are simply a one-step process. And what I want to draw your attention to here is that we've got, enzyme A, we got molecule A that's going to be converted by enzyme 1 into product B, and then product B becomes the next reactant for enzyme 2, which turns B into product C, which then becomes a reactant for enzyme 3 to turn to product D. So I think that you understand it first and foremost on the reason why I'm showing you this is that it's important for you guys to realize that the product of one reaction can become the reactant for the next. And that's really just a big concept, is that A is going to become B. So A, being the reactant, gets turned into the product B. But product B is then the reactant for the next chemical reaction using enzyme 2. So that the product B becomes the reactant for the next step in this metabolic pathway. And then B becomes C, C is the product, but then it becomes the reactant for enzyme 3 to operate on to form molecule D. Then molecule D is the reactant that is being worked on. So at least getting that, and we're going to talk about these molecules in terms of their role within the metabolic processes. But we'll also draw your attention here to a buildup of E. And that's because enzyme 5 is not functioning. So one of our enzymes, one of our proteins that speed up chemical reactions is not working within this metabolic pathway. And without enzyme 5, we can't convert E to F. And so we start to get a buildup in E. Okay, and so obviously this is going to influence how we grow and metabolize, because if we have a buildup in a byproduct that should be converted into another molecule within the metabolic pathway, clearly our cells are going to have to cope with this mechanism. So energy and metabolism go hand in hand. And when we talk about metabolism, we can't talk about one step, we have to talk about multiple steps. Okay, and so it's funny because our cells essentially have to traffic all these different pathways. And so I found this diagram on the left of the screen. This is the actual diagram of every single metabolic pathway associated with the breakdown of glucose. So these are all the pathways that are connected essentially to cellular respiration. And it's these dark, let's see, find this. Let's change the thickness. I know what I'm doing. Here we go. You can see, oh, or maybe you cannot. Oh, that's lame. You can see that here, that was just terrible. My apologies, kids. This dark part in the center is the overall metabolic process. You can see the dark marks here. This is the overall metabolic process for extracting the energy for glucose, but you can see how all of these other metabolic pathways are connected to glucose. And you have to understand that our cells are essentially acting like a stoplight, much like this one I found here. And don't worry, that's not real. You can imagine that that would just be a terrible, terrible thing to have to deal with when you're driving on the street. But my point of this is that inside of our cells, when we're doing metabolism, when we're doing all this stuff, looking for and utilizing the energy the right way, it is a daunting task. Okay? So here we talk about essentially the ideas of metabolic pathways, and we hinted at that in the previous slide, that it has to be a sequence of enzymatic reactions where the reactant A is going to be converted into a product B, but then that product can then act as the reactant in the next step in the pathway. And that anytime an enzyme is not functioning appropriately, we can have a buildup in concentration of one of those metabolic products. We often refer to those as intermediates. intermediates, intermediates, because they are the product of one reaction, but then they become the reactant for the next. So that's what a metabolic pathway is all about. And there are two basic types. There's catabolic and anabolic. Catabolic pathways, just think of catastrophe, and these are going to be pathways that break things down, and they're also going to be the type of pathway that releases stored energy. So catabolic, think catastrophe, thinking of breaking down molecules and releasing stored energy. On the flip side of that coin, of course, would be the anabolic pathway, and an easy way to remember this is just think of anabolic steroids. Anabolic means to build up. So an anabolic pathway simply means a pathway that is going to build molecules and therefore will require an input of energy. So both catabolic and anabolic pathways are forms of metabolic pathways. Catabolic pathways, of course, being to break things down. Anabolic pathways, of course, to build things up. But they are both involve multiple enzymes and these intermediates. The best example for a catabolic pathway, can anyone think of what it might be? The best example of a catabolic pathway is going to be cellular respiration, us breaking down glucose. And then the best anabolic pathway that you might think of in nature is going to be, hopefully you're thinking photosynthesis, or the process of generating or building glucose. So of course these are glucose-specific pathways, but anytime that we're breaking down any biomolecule, it's catabolic. Anytime that we are building up or making any biomolecule, it is going to be anabolic. Now obviously this has to do with the different types of energy that are involved. In other words, we have to obey the laws of thermodynamics. We have to understand what types of energy are being stored and being used in order to do the work that our cell needs. So the work of life depends on different types of energy. Energy is simply the ability or the capacity to do work, to supply heat, or to cause change. You know, we think of work as in physical labor or as in studying, but that all boils down to the cellular level that our cells require energy to do these processes, to be able to grow, to be able to repair, and to be able to reproduce. And for order for us to do all of that on a cellular level, and then of course on a tissue, organ, and then organ system, organism level, that energy all is doing the same thing. The ability to do work, to supply heat, or to cause change. We'll learn, of course, and I think that you already know that any energy stored in chemical bonds is going to be referred to as potential energy. So the energy that is stored. So when we talk about chemical bonds, a carbon-to-carbon bond, a carbon-to-hydrogen bond, or any non-polar covalent bond, potential energy is stored there. Remember, stored energy, like in carbohydrates and in fats, that's going to be the potential energy that our bodies need. Stored potential energy. It's often referred to as energy based on position. You can think of this as when I stand up on the table, I have the potential to fall down. Or even more so here, a diver has more potential energy on the platform than in the water. Okay, so up here, the diver has a lot of potential energy. My apologies for, I keep going back and forth between all this stuff. So high PE. And I'm terrible at doing it because I'm at home, so it's not my smart board. High potential energy on the diving board. He has the potential to do work because he has the potential to go down. Simple and straightforward. Okay, so he has high potential energy there. When that energy, when that diver, or when this high potential energy, this energy based on position, changes, we do not destroy the energy, we simply convert it. This is the law of thermodynamics that we have to pay attention to. The diver has potential energy to move. Think about the valence electrons in any atom within the molecules. They are the higher the outermost electrons, they have the greatest amount of potential energy because they've been excited up to that state, they form that chemical bond and they're storing the energy there. What happens when we break that chemical bond? So we've got this molecule. What happens when we break that chemical bond? We're going to release that energy. But that energy will no longer be potential energy. Rather, that energy is going to be released as kinetic energy, aka the energy of motion. So this is thermal energy. This is temperature. This could be molecular motion. This is the idea of the energy of motion. What happens to those electrons once their bond has been broken? They don't get released everywhere. Those electrons that are up in those valence, those outermost valence shells are going to drop back down. They literally move. So on a subatomic level, what was up must move back down. Okay? On an organismal level, the energy based on positioning is then going to be converted into energy based on motion. When the diver jumps, he loses potential energy, but gains kinetic energy. So there's no loss of energy, really, it's an energy conversion. The diving converts the potential energy into the kinetic energy. Down in the water, you have less potential energy than you did up at the top of the platform. So stored potential energy, it gets converted into kinetic energy, which is the energy of motion, lowering your potential. And the only way that you can get back up is by climbing back up the ladder, which requires an input of energy. And that's sort of what we want to look at here. This process is a release of energy. Some energy is going to come out of this process. Okay? The potential at high potential energy up here, low potential energy down here, and in between, sorry y'all, this potential energy is converted into kinetic. And the process can start all over again by an input of energy here. Okay, so hopefully you guys are starting to see the ideas here. Is that the analogy here is that a diver jumping off of the top of the diving board is releasing energy. Some of that energy is going to be lost as heat is going to get converted into kinetic energy, and you will have low potential energy at the end of this entire reaction. That's the idea of a catabolic pathway. It would be akin to a catabolic pathway. in order to get back up to the platform, you have to build up your potential energy. So the input of the energy going into climbing up the platform is, of course, going to be an anabolic pathway. And so those are sort of where we're going with these ideas here. So we can also refer to as kinetic energy as thermal energy, and we can also refer to potential energy as stored chemical energy. Chemical energy is just the potential energy within the chemical bonds. So there's a variety of different pictures here. The cheetah at rest is clearly showing us stored potential energy. When the cheetah gets up and runs, it's a matter of movement or kinetic energy. The water behind the waterfall, clearly high potential energy, converted into high kinetic energy as the water comes down. So here we've got high PE here. Oh boy. And then high KE here, or kinetic energy, because the water is losing its potential and gaining motion. Okay, you can also think about a car sitting still. You know that you have stored potential energy because you put gas into the vehicle. So the gas sitting there in the garage or at rest has stored potential energy in the chemical bonds of the gas that's in the gas tank. You turn the ignition switch, which means you put a little bit of energy in there. You cause a release of stored potential energy, and our engine converts that into the kinetic energy of motion. Okay, so this is where we're going here with different forms of energy. My apologies for drinking coffee, but it's my soft kitty cup from The Big Bang Theory. So, and it's a Sunday morning at 10, so I need the caffeine. So the laws of thermodynamics. The bottom line, guys, is that we know energy cannot be created or destroyed. It can only be transferred or transformed. So we really have to focus in on the idea of thermodynamics. Dynamic meaning, change, thermo in reference to temperature, but of course the motion and the type of energy. So we have to be able to transform energy. That's what this is all about. And thermodynamics is the study of energy transformations in matter. Matter is anything that occupies space and has mass. We're talking about what's happening inside of our cells, what's happening inside of our tissues, what's happening inside of our bodies, okay? The system will always be a matter, the matter that we're looking at, the matter under study. Excuse me. The surroundings are going to be anything and everything outside of that system. A closed system is isolated from the surroundings. A lot of times when we do experiments, we're looking at creating a closed system. However, we, and most of the things that we're talking about, are going to be open systems where energy transfer can occur between the system and the surroundings. So for us, it could be between our cells and other cells, it could be within our body and our environment, or we could even take it on the larger level where it's the biosphere, the Earth, and its surroundings being the universe. Okay? So we're talking about thermodynamics in reference to a system, which is the matter under study, the surroundings, which is everything outside of the system, and this shouldn't shock you because we saw two different environments before in Chapter 7, so we're just talking about this in terms of the energy here for Chapter 8. The first law of thermodynamics and the second law of thermodynamics. The bear is eating and consuming food. Okay? Here, the bear is actively respiring, releasing CO2 and water, but also releasing heat. And so we're going to actually talk about what the two laws of thermodynamics are. The first law of thermodynamics is simple. Energy can neither be created nor destroyed. It can only be transferred or transformed. Remember that we've discussed the idea that energy is a one-way flow. It comes in from the sun, it goes to the plants store it. They use that energy to store in chemical bonds. That's thermal energy, that's kinetic energy coming from the sun, because it's energy of motion, those photons of light coming in. Plants convert that energy into stored potential energy. So the kinetic energy, that thermal energy coming from, and light energy coming from the sun, That is kinetic energy that plants can convert into stored potential energy in the form of chemical bonds. We then, of course, eat plants or eat organisms that eat plants, and we break those bonds. Okay, so start thinking about this. When plants convert light energy into chemical energy in, or the potential energy in chemical bonds, is this catabolic or is it anabolic? It would be anabolic, to build glucose, photosynthesis. We then, in turn, eat the plants or eat the animals that have eaten plants because we need that energy. And so the energy, in this case, we are going to take the molecules, we are going to break those bonds and release that energy so that our cells can use them. So we break the chemical bonds, which is catabolic. We release that stored energy to use for ourselves. Because remember, energy can only be a one-way flow. So energy can be transferred or transformed, but it cannot be created nor destroyed. This is the law of conservation of energy. So as this energy is traveling one way through the ecosystem, one way through the environment, we use it to recycle. So the plants take in sunlight and our CO2 and make glucose. We in turn take the plants, break it down, and release, the plants produce glucose and oxygen. We take that oxygen along with the glucose, break it down so that the plants then have CO2. Understanding, guys, that this one-way flow of energy is not, you can't argue against it. It comes in and it goes out. Okay? But the nutrients are going to recycle. The carbons, the oxygens, the hydrogens, those are being recycled. So this is the crux of it all. There is a constant energy flow in our systems that we're dealing with. And we cannot destroy it, we cannot create it, we can only convert it or transform it. So energy can only be transferred or transformed. The kick of all of this is that energy transformations, energy transferals are not 100% efficient. Sadly, our little cellular engines are inefficient at this transfer, and we will always lose some energy back out to the environment, hence the one-way flow, and that energy is typically going to be released as heat or more kinetic energy. Every energy transfer or transformation increases this entropy or randomness in the universe. Entropy or randomness is disorder. There is no way around this. The first law states that energy cannot be created or destroyed, but can be transferred or transformed. Since this energy transformation, the first law, is not 100% efficient, it implies that energy is going to be released from the system back out to the surroundings. So the second law of thermodynamics says that because these energy transformations are not 100% efficient, we will always lose energy to the environment, to the universe, and this kinetic energy will increase the randomness or disorder, aka entropy. I'm going to slide past this slide only because I think that you guys pretty much understand that the first law states energy is neither created nor destroyed, it is simply transferred or transformed. A water molecule at the top of a waterfall has higher potential energy. As it falls down the waterfall, its potential energy, or its energy based on position, decreases, and this is converted into the kinetic energy or the energy of motion. When that molecule gets down to the bottom, it's fairly straightforward and easy to see. I'm not really sure why that little guy is there. It's fairly easy and straightforward to see that the bottom of a waterfall is not quiet because sound energy is being released. Heat energy is actually being released. It's not boiling and bubbling, but water vapor is escaping because there's a lot of kinetic energy that's being released. And it's also mechanical energy, and we humans, as brilliant as we are, have sort of taken advantage of hydroelectric power to make the things that we need. So high potential energy at the top of a waterfall, that potential energy gets converted into kinetic energy of motion, and by the time it gets to the bottom, there's no PE, and that kinetic energy, that energy of motion, is really being released as sound, heat, and mechanical energy. Same idea over here in the electrons in their outermost shells. When we add energy, we can move the electron from one shell to another. When we break a chemical bond, for example, and that's essentially what this is all talking about. In this case here, when we break a chemical bond, this electron has to move back down to the nucleus. And as it does so, energy is released. And energy, so it's released to the environment, that's the second law, and the potential energy that it had here becomes the kinetic energy or the energy of motion. So you can see the conversion of potential into kinetic, and in that conversion it is not 100% efficient, and we lose some of that energy back out to the surroundings. So PE to KE, this is our first law of thermodynamics. The second law is saying simply this: because energy conversion is inefficient and it leads to disorder, the increase of disorder in our universe is always increasing. Energy is always increasing. Entropy. Entropy, 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 entropy is always increasing in the universe. Always, always, always. During every energy transfer, some energy becomes unusable and it's lost. Remember, it's not created or destroyed, it's simply lost to the environment. Random molecular motion. Most energy is lost as heat. So consider this. When you're sitting on a couch and you're watching a movie and you get up, you know that that spot on the couch is warm because you were just sitting there. And as you were sitting there, your cells were performing cellular respiration. They were converting the stored potential energy into energy that the cells could use to grow, repair, reproduce, or to metabolize. But some of that energy is not going to make it. It is going to be released as heat to the surroundings. It explains the temperature regulations that we see in the classroom. I've always opened the windows, it gets too hot, I'm trying to regulate. It also explains why we radiate out heat. The entire planet radiates out heat. Our atmosphere traps some of that heat, and it gives us our climate. Most usable forms of energy get partly converted into heat. This is random molecular motion. Each time energy is lost during a transfer, the universe becomes more disordered. Examples of the second law in action. Those of you who are starting to drive, you will eventually notice that your car becomes disordered. It becomes a mess. You might start off, it's nice and clean, but then as you are driving around and you just kind of throw stuff in the back, you forget to do that, you go to the drive-thru, you just throw the trash on the floor, suddenly disorder occurs. It's the same reason why you could argue to your parents that you never really should have to clean your room. No matter how organized you keep that room, the entropy or disorder will always increase, even when you're not there, because slight variations in the molecular motion in the environment of the room will cause a dust particle to move from one location to the next. But of course, no matter what, there's going to be a day where you run into your room, you throw something on the ground, you grab something else, you didn't make your bed, disorder happens. Disorder is the way of the universe. No matter what, because energy transfers and transformations are not 100% efficient, the second law states that disorder in the universe will always, always, always increase. But what does this mean? What does it mean that there's always going to be entropy increasing? Can't I organize a certain area? Can't I clean my house? Can't I clean my room? Can't I clean my car? Yes, you can establish order in a localized sense. But how were you able to do that work? You had to break down biomolecules and release heat. So the heat that you're releasing or radiating out from your body is causing molecular motion in the dust particles or the atoms in the atmosphere, and thus, no matter what, even if you have localized order, you are still contributing to the overall disorder of the universe. Now, one thing we also want to kind of highlight here is the idea that it's a negative change in free energy. And it kind of comes into question, what is the idea of free energy? So we want to keep this idea in the back of our minds, okay? Because in order for the second law to make sense, we have to enter into this idea of something being spontaneous or spontaneity. This idea of entropy explains why certain processes occur. A spontaneous process, a spontaneous reaction, is simply a process that can occur on its own without an input of energy. Things rust. Explosions, they tend to be spontaneous. Any reaction that increases the entropy in the universe could be considered as spontaneous. For a reaction or process to be spontaneous, it must increase the entropy of the universe. Spontaneous reactions occur spontaneously because in its process it is pretty much satisfying the second law of thermodynamics. You'll notice that these spontaneous reactions tend to be releasing energy, which means that energy is being released and that this is a catabolic process. So many catabolic pathways or catabolic processes tend to be spontaneous as long as they increase the entropy of the universe. So spontaneity in reactions has a qualifier of must increase the entropy of the universe. Living systems can organize or bring order to the disorder. We create ordered structures inside of our cells from disordered molecules, right? Plants can make glucose. We can store glucose. And we can not just store the glucose, but we can store the glucose as glycogen, okay? Cells can create ordered structures from disordered molecules. Plants take CO2 and water and energy to make glucose. But cells are also very, very good at taking organized forms of matter and energy from the surroundings and replacing them with less ordered forms. We take glucose, a nice ordered form, stored potential energy, and oxygen. We take those and we destroy the glucose by breaking it up into its components of carbon dioxide, water, and energy. One glucose molecule is ordered. 6 carbon dioxide and 6 water molecules are not ordered. Even though we can create some type of localized order, the process of us doing so has led to a more disordered universe. The evolution of complex organisms seems to sort of violate the laws of thermodynamics, but they don't. Because even if I can decrease the entropy on my own, as I do that, as I decrease the entropy of my surroundings, I'm still contributing to the entropy of the overall universe. Anabolic processes decrease entropy. Catabolic processes increase entropy. Oh, Dr. Higgins, say that again. All right, Pear Bear, I'll make you a new one. Sorry, Pear, that was just my way of making you... Oh, what just happened? No. If anabolic processes decrease entropy, then it makes total sense that catabolic processes increase entropy. And this shouldn't surprise you. Catabolism creates disorder, catastrophe. Anabolism creates localized order. And there's a balance, but there's always an increase in entropy. And so I think one more slide on this little Camtasia and we'll be good. Consider now the second law of thermodynamics. High potential energy at the top of the waterfall. High potential energy in glucose. This is glucose. I think you guys can see that. All group order, send to back. All right. See, I'm this crazy even when I'm not in the classroom. High potential energy, more order in glucose. We take oxygen. We create disorder. High potential energy, stored potential energy. We release energy. Remember, no energy conversion is 100% efficient. We get 12 molecules as opposed to one ordered molecules. There's less potential energy. There's less order. And the energy has been released. Now the trick here, guys. Where does the energy that is released go? We don't just automatically let it go back out to the environment. I'm sorry, this is same basic idea over here. Diving board, diffusion across a membrane that we talked about in the previous chapter, and chemical reaction. But here's the parting note on this for these first 10 slides is this. If what we're doing is creating a more disordered environment, we're always releasing this energy. Why is it that we have to keep doing what we do? There's energy stored in these chemical bonds. We're going to break them down. We're going to create disorder. That energy is being released, but it doesn't immediately go out to our environment because we still have some tricks inside of our cells. We still need to find a way to harness that energy as it's going that one-way flow. And so we're going to pick up on the idea that as we release the stored potential energy, we have evolved an amazing molecular mechanism to temporarily store that energy so that we can perform cellular work.